before the clocks are green. There is a particular quality to the dark at this hour, not the absence of light exactly, more like the presence of something that light usually covers up. The room has a weight it does not have in the afternoon. Your body knows it has been here before, lying still, breathing slower than you think you are breathing, at the edge of something. And somewhere out there, not metaphorically, actually out there, past the ceiling and the atmosphere and the distance your mind gives up trying to picture after a while, the universe is doing something it has been doing since before the planet existed, quietly, without anyone to notice it or name it or feel strange about it. This is the Sleepy Science Channel. People who keep it going, you know who you are, and so do I. If you have ever sent someone here at 2 a.m. because you thought they needed it, that matters more than I usually say out loud. There is a question at the center of this series that cannot be answered yet. Not because the science is incomplete, though in places it is, but because the question is the kind that has to be lived with for a while before it opens properly. The question is something like, what happens when the universe runs out of things to do? Not dramatically, not all at once. More the way a conversation runs out, or a fire does, or a person does, eventually. A long, slow, structural quieting that has been in progress since the first second, and will continue past any number we know how to say. That is what this is about. We will not get to the end tonight. We are starting somewhere much earlier than the end, in a place that might feel almost familiar, where the clocks still run and the stars still hold their shapes, and everything seems, from where you're lying, roughly fine. It is not quite that. The thing that undoes the universe is not a force from outside it. It is a property the universe has always had, built into the way matter and energy behave when left to themselves long enough. The property is called entropy. That word will not appear again in this chapter, not because it is a difficult word, it is not, but because naming it once and then letting it go is the more honest approach to what it actually is. Entropy is not something you can hold in a definition. It is something you recognize when you watch what happens to things over time, which is, it turns out, always the same general thing. They spread out. They even out. They move from a state where something was possible toward a state where that same thing is no longer possible, and they never on their own move back. You have been watching this your entire life. You just had no reason to notice it had a name. A hot cup of something on a table at night. You made it, and then forgot about it for 20 minutes, and now it is not quite what it was. The heat that was concentrated in the liquid has been distributing itself into the room, into the table surface, into the air you are breathing. The cup is not broken. The liquid is not gone. But something has happened that will not unhappen. The heat has gone from arranged to scattered, from useful to ambient, from somewhere specific to everywhere in general, and everywhere in general is the same as nowhere in particular. This is not a small thing. This is the operating principle of the universe wearing a domestic disguise. Every time anything warm touches anything cooler, the same negotiation happens. Every time a gas expands into a new space, the same negotiation happens. The molecules do not decide to spread out. They do not prefer disorder to order, despite what you may have heard. They just move, randomly, and when you have enough particles moving randomly in enough directions, the probability of them all moving back to where they started becomes so small that it is, for every practical and impractical purpose, zero. The universe is not sliding toward disorder because disorder is somehow winning. The universe is sliding toward disorder because there are so many more ways to be disordered than to be ordered that random motion almost inevitably gets you there. A dropped glass does not want to shatter. It just has far more ways to be shattered than to be whole. The direction of time, the reason you remember yesterday and not tomorrow, the reason the cup cools instead of heats, the reason a broken thing stays broken. All of it traces back to this. The universe started in a state of extraordinary, almost incomprehensible order, and it has been moving away from that state ever since. Not running away from it, drifting, the way smoke drifts from a candle after you blow it out, not toward anything, just away from what it was. Consider how long a process has to run before you notice it is running. The heat leaving your cup happens in minutes. You can watch it happen, in a way, if you press your hand to the ceramic at intervals and feel the difference. But the same process happening at the scale of stars takes millions of years per degree of change, and at the scale of the universe it takes time scales that are not really numbers anymore. They are more like notations for the place beyond which the human mind stops producing images. The process is the same, the duration is not. This is the part that requires some sitting with. The universe running down is not happening fast, it is not happening slow. It is happening at a pace that makes slow seem like a hurried thing. The stars you can see right now have fuel, most of them, the ordinary ones, that will last billions of years. The universe is approximately 14 billion years old. The longest-lived stars will burn for 100 times that. When those stars go, the universe will be in a state that would be unrecognizable from here, and that state will still be early. It will still be nowhere near the end of what entropy has planned. Planned is the wrong word. Entropy does not plan. It just continues. You feel time in your body in a way you do not feel it as a concept. The tiredness you have right now is time, not poetically. The literal chemical accumulation of a day, the build-up of adenosine in the brain, the slow statistical drift of your body from the high-order state of morning toward the lower-order state of sleep. Entropy at biological scale. The same process, the same direction, the same impossibility of reversal without external input, which in your case means sleep, which means your body running another process to restore the order that the day spent undoing. The universe does not sleep. It does not have a mechanism for restoring order the way you do. When the heat leaves the cup, there is no process that puts it back unless you return to the kettle. When the universe radiates energy into its own increasing dark, there is nowhere for that energy to go that allows it to become useful again. It just spreads into the expanding space that is itself, still expanding, carrying everything further from everything else, thinning the warmth of the cosmos the way water thins a dye, not removing it, just distributing it until the concentration becomes impossible to detect, impossible to use, impossible to notice. There is a word for the state at the very end of this process, the state when the temperature everywhere in the universe has equalized to the point where no further transfer of energy is possible, where no event can happen because no event can find a gradient to run down, where the universe has, in every sense that physics can measure, finished. But that word is for a later chapter. This chapter is about the beginning of the process, and the beginning is right now, and it has always been right now, and you have been inside it your entire life without feeling it move. The question of why the universe started ordered enough to be doing this at all, that is a question this chapter is not going to answer. Not because the answer is unknown, though it is partially unknown, but because sitting next to it for a moment is more useful than solving it. The fact that the universe began in a state of extraordinary low entropy, that it was, at its start, arranged in a way that allowed every star and planet and organism and late-night listener to exist, is something physics can confirm, but not fully explain. It is one of those facts that sits at the edge of science and something else, and the edge is not uncomfortable. But it is honest about what it does not know. What physics can say is this: the direction was set from the first second. The arrow of time, the reason events proceed in one direction and not the other, points away from that original arrangement and has been pointing that way ever since. You are somewhere on that arrow right now. So is the cup. So is the star whose light is coming through your window, or would be if the window were open and the star were above the horizon, which it may or may not be. The star is losing heat too, just much more slowly and all at once, and eventually not at all. But the direction is the same as the cup. The direction is always the same. What entropy actually feels like. From the inside right now, inside your left hand, approximately 37 trillion cells are doing something. Not in sequence, not in coordination exactly. More the way a city does something at midnight, most of it quiet, some of it intensely active, all of it proceeding without any central awareness of itself as a whole. Your hand does not know it is a hand. The cells inside it do not know there are other cells. Each one is just running its own version of the same general process, taking in what it needs, releasing what it does not, maintaining a state of internal order that costs energy to maintain, and will, one day, stop being maintained, and that will be the end of the cell. And eventually the accumulation of many such endings will be the end of you, and the molecules that were you will go on to be parts of other things, spreading out, distributing, moving in the direction that everything moves. This is happening right now, in your left hand, while you're lying still. The process that keeps a cell alive is, at its foundation, a fight against the tendency of things to even out. The cell has a different chemical composition on its inside than on its outside, and it works constantly to keep that difference intact, because the difference is the thing. Without the difference, there is no voltage across the membrane, no signal, no function, no cell in any meaningful sense. Just a bag of molecules with the same concentration as the bag of molecules next to it. The machinery that maintains this difference is not simple. Proteins embedded in the membrane act as pumps, moving ions against the direction they would naturally go, spending energy to preserve an arrangement that would otherwise dissolve. Sodium wants to come in, potassium wants to go out. The pumps say, "Not yet. Not yet, not yet." For as long as the cell lives, the pumps say not yet, and the moment the energy runs out, or the pumps fail, or the membrane tears, the ions go where they were always going to go eventually, and the difference collapses and the cell goes quiet. This is what life is, at its most mechanical. A temporary, energy-expensive refusal to even out. A local exception to the general rule, maintained at cost destined to end. You have been making that exception for decades. Every cell in your body is making it right now. And still, despite this enormous ongoing expenditure of energy to stay ordered, you are not winning against the broader process. You are participating in it. The food you eat, which is itself organized chemical energy, stored order, sunlight that was captured by a plant and locked into molecular bonds, gets taken apart inside you, and the energy released is used to maintain your own order for a while, and the waste products are released, and those products are more disordered than the food was, and the net result of you existing is that the universe has moved overall, further in the direction it was already going. Life does not reverse the process. Life is part of the process. This is not a pessimistic fact, or it does not have to be. It is just accurate. The sun is the source of almost all the order on this planet, and the sun is spending itself, and we are how it spends itself, and the spending is the point, or at least it is the mechanism, and meaning, if it exists, has to be found somewhere inside the mechanism because there is nowhere else to look. There is a sensation that might be familiar if you have ever sat very still in a warm room and felt the air against your skin and noticed, really noticed, that the warmth is not coming from outside you but from inside you, your body producing heat as a byproduct of all the maintaining it is doing, radiating it outward the way everything radiates outward, the way everything participates in the general dispersal without being asked. You are not just warm, you are a source. You are, in a small but real sense, a star, a place where organized energy is being converted and released, where the local concentration of order is being spent to maintain a temporary, improbable and specific arrangement of matter. The scale is different. The principle is the same, and the star, like you, is working through a finite supply. The star does not know this. You, lying there, might. What it feels like from the inside is mostly just being. The hunger that comes from having spent energy and needing more. The tiredness that comes from all the maintaining. The particular quality of warmth that is your own warmth, not the room's, not anyone else's, yours. These sensations are not poetic descriptions of thermodynamics. They are thermodynamics. They are what the second law of thermodynamics actually feels like when it is happening inside a body that is conscious enough to register it. The law does not feel like a law from in here. It feels like thirst. It feels like the specific heaviness of an arm that has been still too long. It feels like the way a deep breath reorganizes something that had begun to scatter. And when you exhale, the carbon dioxide that leaves your lungs is carrying away some of the disorder your body produced while you were thinking about this. The breath completes a small transaction in the universal accounting. You go on. The universe goes on. The direction does not change. The direction is patient in a way that living things, by definition, cannot be. Here is a thing that is technically true and almost never said. The reason you will die is the same reason the universe will end. Not the same mechanism, not the same time scale, but the same direction, the same underlying tendency, the same impossibility of running an ordered system indefinitely without a source of energy that is itself finite. You and the universe have this in common. You are both, at this moment, somewhere in the middle of the process, neither at the beginning nor at the end, both spending what you were given to maintain a shape for as long as the shape holds. The universe's shape is everything. galaxies and voids and the slow movement of matter through expanding space, the gradients of temperature between stars and the dark between them, the complex structure of everything that exists. Your shape is the particular arrangement of everything you are, right now, in this room, in this position, with this specific pattern of electrical activity in the neurons that are, at this moment, receiving the idea that you and the universe are doing the same thing. Neither shape will hold forever. Both shapes are, right now, holding. The stars are lying to you, slightly. Look up on a clear night, and you're about to receive information. That is what looking at the sky is. Not an experience of the present. A delivery from various points in the past, arriving simultaneously, as if time had been folded and several different moments were all landing on your retina at once. The star does not know you are looking. The light left before you existed. In some cases, long before. This is the fact called the look-back time. Every point of light in the night sky is a message from a different moment in history. The moon's light is about 1.3 seconds old. The sun's is 8 minutes. The nearest star beyond our solar system, Proxima Centauri, is showing you what it looked like roughly 4 years ago. The stars visible to the naked eye range from a few light years to a few thousand light years distant. The Andromeda Galaxy, faintly visible as a smear of light on a dark night, is showing you what it looked like 2.5 million years ago. That light left its source before humans existed. It has been travelling uninterrupted ever since, and it ends on you. There is something strange about being the endpoint of a 2.5 million year journey that the traveller was not aware of. The light does not know where it is going. It is not going anywhere in particular. It is just going, the way photons go, outward in all directions from their source, some of them headed toward nothing, some of them absorbed by gas clouds, some of them landing on the surface of a planet that developed eyes, which then developed the habit of looking up. You are the coincidence at the end of that trajectory. Most of the light from Andromeda is going nowhere useful. Most of it will cross the universe without ever touching anything. The fraction that reaches Earth is vanishingly small. The fraction of that fraction that reaches an eye on a particular night is smaller still, and yet there it is. The faint smear, still travelling, still arriving. What the middle distance of the night sky gives you, the stars you can actually name, the constellations, the things your eye organizes into shapes, is a picture that is not internally consistent in time. Orion, if you are in a hemisphere that can see Orion, is not a cluster of objects at the same distance from Earth. Each star in it is at a different distance. When you look at the shape, you are seeing several different moments simultaneously, some of those stars as they were hundreds of years ago, some as they were thousands of years ago, all composited by your visual system into a single image it interprets as present. There is no present in what you are seeing. There are only pasts, various and overlapping, arranged by your mind into the shape of a now. The constellation does not exist as a shape except from here. From any other angle, from any other point in space, those stars would not align into that figure. The shape is something your position in space produces from objects that have no relationship with each other. Orion is a perspective, not a thing. This is the part worth sitting with, so it gets more room than usual. What you call the night sky is a projection. Not in the suspicious sense, There is no deception involved, and no one is hiding anything from you. But in the literal geometric sense, the three-dimensional arrangement of stars spread across vastly different distances gets flattened by the act of looking into a two-dimensional surface that your mind reads as a map. And maps are always simplifications. Maps lose one axis. In this case, the axis they lose is time. When you navigate by the stars, as humans did for most of human history, you're using a map drawn from light of many different ages. The navigational information is perfectly accurate. The positions work. The stars are where they appear to be, relative to each other and relative to the horizon. But the map is not of the present. It is of a composite of many pasts, rendered stable enough by the extreme distances involved that it changes only imperceptibly from century to century. The stars seem fixed. The sky seems permanent. Both are illusions produced by scale. Some of the stars you use to navigate have already ended. Their light is still arriving. The news has not caught up yet. Betelgeuse, the bright orange star in Orion's shoulder, is between 400 and 500 light-years away. It is also a massive red supergiant in the late stages of its life, expected to explode as a supernova at some point, possibly within the next 100,000 years, possibly sooner, possibly in a sense already having done so, and the light simply not yet arrived. When Betelgeuse goes, and when that light reaches Earth, the explosion will be visible in daylight. It will be brighter than the full moon for weeks. It will be the most dramatic thing the naked eye sky has offered in recorded human history. And it may have already happened. Right now, if Betelgeuse exploded 400 years ago, the light from that explosion is 400 light-years into its journey toward us, and will arrive in roughly 100 years. Or it exploded 300 years ago, and will arrive in a few decades. Or it has not exploded yet. We cannot know. The information is still in transit. The star you see when you look at Orion's shoulder may not be there anymore. Come back to the smaller fact. The personal one, the 8 minutes that separate you from the sun. Every morning the light that wakes you left its source 8 minutes before it arrives. The sun you see is always the sun of 8 minutes ago. If the sun were to simply stop, which it will not in any sudden way, you would have 8 minutes of not knowing. 8 minutes of a sky that looked normal, while the source had already gone. 8 minutes of light travelling toward a planet that was about to find out. This is not a frightening thought. It is just a true one. The gap between event and knowledge is built into the universe. It is not a failure of information systems. It is the consequence of light having a speed and space having a size, and those two things being what they are. You live inside that gap. Everything you see is already the past. The stars are not lying exactly. They are sending the most accurate report they can. The report just takes time to arrive, and time at these distances is not a delay you can compensate for the way you can adjust a clock for a different time zone. It is a structural feature of the universe, a consequence of the fact that nothing travels faster than light, and light does not travel instantaneously, and the universe is very, very large. What you see when you look up is real. It is just not now. And somewhere in the universe, right now, something is ending that will take so long to report to us that the civilization receiving the news, if any civilization is there to receive it, will have no memory of a time when the thing that ended was still there. The sky keeps those secrets for a while, it always has. how a universe learns to cool. The universe has already done most of its cooling, not in the way a room cools, not in a way you could have felt as a change. The cooling of the early universe happened in the first seconds and minutes after the Big Bang, and was so rapid and so extreme that the word cooling barely covers it. In the first fraction of a second, temperatures exceeded 10 billion degrees. Within 3 minutes, they had dropped to roughly 1 billion degrees. Within 400,000 years, a span of time that sounds long but is a breath compared to the current age of the universe, the temperature had fallen enough for electrons to settle into orbit around protons and neutrons and form the first atoms, hydrogen mostly, some helium, a trace of lithium. This moment has a name, the recombination epoch. The moment when the universe went from a hot, opaque plasma through which light could not travel, to a cooler, transparent gas through which light moved freely for the first time. The light released at that moment is still travelling. We can detect it now as the cosmic microwave background radiation, a faint hiss of microwave radiation coming from every direction in the sky. The afterglow of the first moment the universe became see-through. Its temperature today is approximately 2.7 degrees above absolute zero. That is how much it has cooled in 14 billion years, from 10 billion degrees to 2.7. But 2.7 degrees above absolute zero is not the end. It is a point on a line that continues. The universe is still cooling. The cosmic microwave background temperature drops as the universe expands, because the expansion stretches the wavelengths of the photons, which lowers their energy, which lowers the effective temperature. The universe will not stop expanding. Current evidence strongly suggests it will expand forever, accelerating as it goes, driven by whatever dark energy is. And as it expands, the background temperature will continue to fall, slowly, very slowly, over timescales that make the current age of the universe look like an opening act. This is the long middle of the story, the part after the dramatic early cooling and before the final darkness, the part we are in now. What does cooling mean at cosmological scale? Not warmth leaving a body, not heat conducting through a surface. Something more structural than that, more about what is possible and what is not. Temperature, at its foundation, is a measure of the average energy of particles in a system. High temperature means particles moving fast, colliding often, transferring energy, making things happen. The early universe was a place where things were happening at rates that are impossible to describe without notation that looks more like poetry than physics. Nuclear reactions in the first 3 minutes, particle-antiparticle creation and annihilation in the first fractions of a second. An environment so energetic that the distinction between matter and energy was not a stable one. As it cooled, certain processes became impossible, too cold to create new matter-antimatter pairs, too cold to sustain the nuclear reactions that formed helium and lithium, too cold for electrons to stay free, so they fell into orbits, and the universe became transparent. Each threshold crossed was a permission revoked. Something that had been possible became not possible, and the universe moved to a new phase, a new set of rules, a new list of things that could still happen. We live in one of those phases, the phase where atoms are stable, where molecules can form, where chemistry works, where temperatures at stellar surfaces are high enough to drive photosynthesis on planets in the right orbits. The phase where life is possible. This phase will not last. The stars are the universe's primary remaining heat source. They are the places where the temperature is still high enough for something to happen. Nuclear fusion in their cores, the conversion of hydrogen to helium, releasing energy that radiates outward and maintains the local environment at temperatures vastly above the cosmic average. But stars have finite fuel. This sun will spend roughly 10 billion years on the main sequence, fusing hydrogen in its core before the hydrogen runs out and the core begins to contract and the outer layers expand and it becomes a red giant. In the far future, it will shed its outer layers and leave behind a white dwarf, a dense, hot remnant roughly the size of the Earth, made mostly of carbon and oxygen, no longer fusing anything, just radiating away the heat it has stored over billions of years. White dwarfs cool, slowly, but they cool. Over timescales of trillions of years, a white dwarf will radiate away its thermal energy and eventually become a black dwarf, a cold, dark object made of degenerate matter, producing no light, emitting no heat, sitting in space as a record of a star that used to be there. The universe will eventually be full of these. The stellar phase, the phase we are in, the phase where stars exist, has an end. The last stars, the smallest and most fuel-efficient ones, red dwarfs burning cool and dim, will live for perhaps 10 trillion years. When they go, there will be no new stars to replace them, because the gas reservoirs that form stars will have been used up, and what remains will not have the density or conditions to collapse into new ones. The lights will go out, not all at once. One by one, over an incomprehensible span of time, the last stars will exhaust their fuel and either explode or quietly fade, and the universe will enter a new phase. Darker, colder, a different set of rules, a shorter list of things that can still happen. There is a texture to the word still that is worth noticing. Not quiet in the way a room is quiet, not dark in the way a room is dark. The post-stellar universe will not be a place anyone is in to notice the dark or the quiet. It will just be the state the universe is in. Objects moving, heat radiating, the expansion continuing. But the dramatics of stellar life gone. No supernovae, no planetary systems forming around new stars, no photons in the visible spectrum streaming across space in quantities that would light anything up. The universe will have learned, by then, that certain forms of expression are no longer available to it. That is a strange thing to say about a universe. It is not wrong. The cooling is not a winding down of activity in the sense of things slowing to a stop. It is a sequence of permissions expiring, and we are watching, from inside one of the most energy-rich and structurally complex phases of that sequence, looking both backward toward the heat we came from and forward toward the cold we are heading to. And the distance in both directions is so large that it barely fits in the same thought. The universe is learning to cool the way anything learns, by doing it and finding that some things are left behind and continuing anyway and never once deciding to. The part nobody talks about in the middle. After the stars go, there is an era that almost nobody names. Not because it is a secret, because it is boring in a way that is difficult to write about, difficult to picture, difficult to care about in the way you care about things that are dramatic or brief or personal. It just goes on. That is its whole character. It just goes on. Cosmologists sometimes call this period the degenerate era. It follows the stelliferous era, the era of stars, the era we are in, and precedes the black hole era. It is a vast, almost structureless span of time during which the universe contains matter, but almost no light, motion, but almost no events, objects, but almost no activity. The numbers involved do not behave like numbers. The stelliferous era, the age of stars, will likely end somewhere around 10 to the power of 14 years from now. That is 100 trillion years. The current age of the universe is approximately 13.8 billion years, or roughly 10 to the power of 10. So the stellar era extends roughly 10,000 times longer than the universe has currently existed. Already this is a number that stops meaning anything when you try to hold it. The degenerate era begins after that and runs until approximately 10 to the power of 40 years from now. This is not 10,000 times longer than the stelliferous era. It is 10 to the power of 26 times longer. The ratio of the degenerate era to the stelliferous era is larger than the ratio of the stelliferous era to a single second. I am not sure I understand what I just said. I mean that in the most literal way. The number has the shape of a number. It does not have the feel of one. What is in the universe during this period? The objects that remain after stars have gone are not nothing, but they are quieter than anything we have experience of. White dwarfs cooling toward black dwarfs, neutron stars, incredibly dense remnants of collapsed stellar cores, slowly losing their rotational energy, growing quieter. Brown dwarfs, objects that almost became stars but never quite ignited, drifting without fusing, and planets, freed from their orbits around stars that no longer exist, wandering independently through the dark. These objects are not doing very much. Occasionally, perhaps every trillion years or so, a very cold brown dwarf might collide with another and briefly reignite a small amount of fusion. An event. Cosmologically speaking, a brief local disturbance in an otherwise unmarked span of time. It would not look like much. It would produce a faint, short-lived flash of light in a universe that has otherwise been dark for longer than stars existed. Nobody would see it. There is something about this era that I find genuinely hard to place. Not frightening, not sad, but hard to locate a feeling for. A universe that is still technically there, still following all its rules, still full of matter and subject to gravity and expanding, but in which almost nothing is happening. A universe in a kind of metabolic state so low it barely registers. Is that the universe resting? Is it the universe waiting? It is neither of those, of course. It is just what it is. A consequence of the stellar era having ended, of the fuel having been spent, of the cooling having progressed to a point where only the coldest and most patient processes still have anything to work with. I keep reaching for an analogy and not quite landing on one. There is a phenomenon in biology called cryptobiosis. Certain organisms, tardigrades are the famous example, can enter a state of suspended animation when conditions become too hostile, essentially pausing all metabolic activity until conditions improve. Their water content drops to near zero. Their metabolism nearly stops. They are not dead. They are not alive in any active sense. They are waiting in a state that is technically possible for them, but represents almost none of what they are capable of. The degenerate era is something like that for the universe. Except the conditions will not improve. The universe is not waiting for something to change so it can resume. The low activity is the new state, the permanent one, the one that will continue until even these quiet objects finish their long, slow processes and the era ends in a new kind of transformation. The tardigrade analogy breaks here. There is no revival. Still. The analogy was almost right for a moment. The thing that finally ends the degenerate era, if current theoretical physics is right, and there is a real uncertainty worth naming here, is proton decay. The protons inside all that dark, cooling matter will, if they do decay according to the predicted timescales, eventually destabilize and break down into lighter particles. All the black dwarfs, all the neutron stars, all the cold wandering planets, all the dark matter that ever was a white dwarf that was ever a star, all of it will slowly come apart at the proton level, releasing a faint trickle of energy as it goes. When the last proton in the last remnant object decays, the degenerate era ends. The universe that remains will be made of the lightest possible particles and photons and the gravitational ghosts of objects that used to be there. It will have been, by then, quieter than anything the word quiet is built to describe, for longer than any unit of time we currently use is built to express, and somehow it will still have further to go. Iron and the long patience of decay. Inside the core of a massive star late in its life, the fusion process is building toward a threshold it cannot cross. For millions of years, the star has been fusing lighter elements into heavier ones, hydrogen into helium, helium into carbon and oxygen, carbon into neon and magnesium, neon into oxygen, oxygen into silicon, silicon into sulfur, argon, calcium, moving up through the periodic table in a sequence that releases energy at each step, energy that pushes outward against the gravitational weight of the star pressing inward, maintaining the balance that lets the star exist. Then the fusion reaches iron. Iron is the end of the road for a reason that is almost beautiful in its simplicity. All the fusion reactions before iron released energy because the products were more tightly bound than the reactants. The nuclear force held the new nucleus together more efficiently than it held the old ones. Making iron from silicon releases energy, but making anything heavier than iron, cobalt, nickel, copper, on up through the periodic table, requires energy rather than releasing it. Iron sits at the peak of the binding energy curve. It is the most tightly bound of all nuclei. You cannot get energy from fusing it. You cannot get energy from splitting it. It is, in a very specific sense, the most stable arrangement of protons and neutrons that exists. When the core of a massive star fills with iron, the energy production stops. The outward pressure vanishes. Gravity wins in milliseconds. The core collapses. But iron's significance to the long-term fate of the universe is not about supernovae. The supernova is the dramatic event, the thing worth noting in the short term. The longer-term significance of iron is quieter and more total. Every nucleus in the universe is, at any given moment, sitting in a state that is either on its way toward iron or already there. The nuclear landscape has a valley at iron, a place of minimum energy, and nuclei above and below that valley, hydrogen and uranium alike, though by vastly different paths, are technically in states from which they could move toward that valley if given enough time and the right conditions. In the very long run, given enough time, this is what happens. Not through fusion in stellar cores, but through a slow process of nuclear transformation that operates over timescales so long they barely qualify as rates rather than geological epochs. The universe, if given enough time, trends toward iron. This is not iron as the metal you know, not a reddish-brown oxide on a fence post, not a dense weight in the hand, not the mineral in blood that makes it taste the way it does. The iron at the end of the universe's nuclear journey is iron as a state. The arrangement of protons and neutrons that requires the least energy to maintain, the resting point that the nuclear force is always very slowly nudging matter toward. Every star that has ever existed has contributed to this process. The stars that have already ended produced iron in their cores directly and distributed it through supernovae or planetary nebulae into the interstellar medium, where it became part of new clouds, new stars, new planets. The iron in the Earth's core, the iron in the hemoglobin in your blood, the iron in the steel in the building you are inside or near. It was made in stellar cores, released in stellar deaths, gathered again by gravity, and is now sitting in the configuration that is more stable than any it has occupied before. It is, in a very specific sense, closer to the end state of the universe than the hydrogen that formed in the Big Bang was. You are made partly of material that is further along the long journey than anything that has come before it. The further nuclear transformations, the slow decay of radioactive isotopes, the eventual decay of protons themselves if proton decay occurs, continue the trend beyond iron toward an even simpler state. The elementary particles themselves, the quarks and electrons and photons that are the final disassembled form of matter. But between iron and that final state, the universe spends an enormous amount of time in the iron-rich degenerate era, with all its cooling black dwarfs and quiet remnants. Those objects are not doing nothing. They are sitting in a deep energy minimum, radiating heat very slowly, their internal structure stable in the way iron is stable, deeply settled, not urgently going anywhere, but still subject to the tiny statistical fluctuations that will, over incomprehensible timescales, cause them to change. The quantum world does not allow anything to be perfectly still. Even in the deepest cold, even in the darkest era, particles fluctuate. Positions are uncertain. States are uncertain. The universe, even at its most settled, continues to search its own probability distributions for configurations it has not yet tried. This is not a hopeful observation and not a desperate one. It is just what happens when quantum mechanics and thermodynamics share a universe with no shortcuts and no entered time. There is something about the iron endpoint that feels like the universe arriving at a preference it had always had. Not a preference in any intentional sense. But the physics has always had this shape, a landscape with a valley, and everything rolling toward the valley slowly with many interruptions across many scales of time and space. Supernovae are an interruption. Life is an interruption. Galaxies are an interruption, in the sense that they are local structures that temporarily organize matter against the general trend before the trend reasserts itself. The valley is iron. The trend is toward stability. The timescale is everything that has ever been called a long time, and then much more. What is strange about knowing this, and it is strange sitting with it, regardless of how many times you consider it, is that the process does not slow as it approaches the valley. There is no declaration, no perceptible change in pace. The universe simply continues moving in the direction it has always moved, accumulating iron in the cores of dying stars, distributing it through space, letting gravity gather it again, cooling it, settling it into the dark. The valley is patient. The valley has always been patient. The valley has been waiting, in the only sense in which waiting applies to a physical configuration, since the first proton formed a second after the Big Bang. Everything has been on its way there ever since. Protons have a lifespan and it is unimaginable. Protons do not decay. This is what you were taught if you were taught anything about protons. They are stable. They last forever. They are one of the permanent things. This is probably wrong. Not certainly wrong. The experimental evidence is inconclusive in a specific and interesting way. We have not observed proton decay, but the fact that we have not observed it does not mean it does not happen. It means it happens too rarely for our detectors to catch. The best current experimental lower bound on the proton lifetime, the shortest lifetime we can currently rule out, is around 10 to the power of 34 years for certain decay modes, which means if protons do decay, they last at least 10 to the 34 years on average before doing so. 10 to the 34 years. Let that land. The universe is 10 to the power of 10 years old. The minimum proton lifetime is 10 to the 34th power years. The proton has been around, if this lower bound is anywhere near the actual lifetime, for a fraction of its life so small that expressing it as a percentage produces a string of zeros longer than this chapter. The decay of a proton is not like the decay of a radioactive atom. Radioactive decay involves the nucleus rearranging itself, a neutron becoming a proton or vice versa, the atom changing its identity. Proton decay, if it occurs, is more fundamental than that. The proton itself, one of the building blocks of matter, one of the two types of particles that make up every atomic nucleus that has ever existed, breaks down into lighter particles, a pion and a positron, in the most commonly predicted decay mode, or other combinations depending on which theoretical model turns out to be correct. After proton decay, there is no proton. There are just the products, and the products are lighter, simpler, not themselves stable indefinitely, until all that remains are photons and the lightest possible leptons. This is where matter ends, not in a black hole, not in a heat death, in the slow, unobserved one-by-one statistical dissolution of the protons in every object that ever existed. Here is the shape of it. You have, in your body, approximately 7 times 10 to the 27th protons. This is a very large number. Even if the proton lifetime is as long as 10 to the 34th years, statistical decay rates mean that somewhere in your body, roughly once every 75,000 years, a proton would decay. If you were alive then, which you would not be. But the atoms that were once yours would still be there in the universe in some form, and the protons in those atoms would still be decaying at that rate. The objects in the degenerate era, the black dwarfs, the neutron stars, the cold wandering remnants, contain vastly more protons than you do. The decay rate scales with the number of protons. A black dwarf containing the mass of the Sun has on the order of 10 to the 57th protons. Given a lifetime of 10 to the 34th years, the entire black dwarf would decay completely in roughly 10 to the 37th to 10 to the 45th years, depending on the exact model. That is the degenerate era ending, not with a collapse or an explosion, with each proton in each cold, dark object deciding, one at a time, at its own statistical pace, to become something simpler. The objects do not notice. There is nothing inside them to notice. What does a proton decaying sound like? Nothing. What does it look like? A faint flash of gamma radiation, undetectable in the surrounding dark. What does it feel like? There is nothing to feel it. This is the thing that is hard to hold. The ending of matter is not dramatic at the scales it occurs. Each individual event is so small, so quiet, so local, that nothing around it changes perceptibly. The object that is decaying goes on looking, from any outside perspective, exactly as it did before, minus one proton, which is indistinguishable from what it was before in any way that matters at human scales. The accumulation of these events over timescales longer than the stelliferous era, by a factor larger than the stelliferous era itself, eventually removes the object entirely. But no single moment is the ending. The ending is a rate, a statistical property, a gradual redefinition of what is there. The universe does not announce when a black dwarf finishes decaying. The last proton in the last black dwarf goes in a flash of radiation that propagates outward into a universe that by then is so diffuse and so cold that the radiation itself will have almost nothing to interact with. It will just travel, redshifting as the universe expands, losing energy, fading. Not even that will mark anything. The number 10 to the 40 is not the proton lifetime. It is more like an address, a location in the sequence of time where something is, an address that corresponds to no city, no country, no civilization, no star, no planet, no body. Just a point on the line that time makes, a point so far from this one that the distance between now and the formation of the first stars is a rounding error by comparison, contained somewhere in the long decimal expansion of the difference. I keep coming back to the fact that the proton has probably been here for a tiny fraction of its existence, that we, matter, life, structured complexity, the ability to wonder about protons, have appeared inside the first breath of the proton's likely lifespan. The stellar era, the age of complexity, the age of everything we know to exist, is the opening. Not even the middle. The beginning. What comes after is not for us. It is not for anything with us in it. It is just what time looks like when you give it enough room. Black holes are the last complicated things. There is a point in the far future of the universe where almost everything that could be called an object has finished its business. The stars are gone. The white dwarfs have cooled to black. The protons in most of the ordinary matter have decayed, assuming they decay, which theory predicts but observation has not yet confirmed. The universe is mostly dark, mostly cold, mostly quiet, a vast space containing a great deal of very diffuse radiation, and the lightest possible particles, and scattered through it at distances that would take light incomprehensibly long to cross, the objects that have outlasted everything else, black holes, not because they are the strongest, not because they are the most exotic, but because of the specific way they hold energy, which allows them to persist long after every other structure the universe ever built has dissolved. A black hole is, at its most precise, a region of space where the gravitational field is strong enough that nothing, not matter, not light, can escape once it has crossed the event horizon. The event horizon is not a surface in any physical sense. No wall, no membrane, just a mathematical boundary beyond which the geometry of space-time points everything inward. An object falling past the event horizon does not feel anything different at the moment it crosses. There is no perceptible threshold. The crossing is not an event, it is a geometric fact, and it is only apparent from outside. Inside, everything converges toward the singularity at the center, a point of the effectively infinite density where current physics honestly breaks down and produces outputs that cannot be taken literally. What happens at a singularity is unknown in a genuine sense. The equations fail. The universe may have an answer that our current description cannot provide. This is not a comfortable position for physics to be in. It holds it anyway, because intellectual honesty is more useful than the comfort of a wrong answer. Black holes feed on whatever passes close enough to be captured. In the current era, while gas and dust and stars exist, massive black holes at the centers of galaxies feed actively, consuming material, heating it as it spirals inward, producing some of the most energetic phenomena in the observable universe. Quasars, active galactic nuclei, jets of relativistic plasma shooting perpendicular to the accretion disk at nearly the speed of light. Enormously active, enormously bright. In the far future, this feeding ends. The gas is gone. The stars are gone. What remains are the black holes themselves, gradually consuming whatever wanders into their gravitational influence. The occasional cold remnant object, a wandering planet or a black dwarf passing too close, and slowly, incredibly slowly, doing something else. They evaporate. The evaporation of black holes is called Hawking radiation, after Stephen Hawking, who proposed it in 1974. The mechanism is a consequence of quantum field theory and curved space-time, and it is both well established theoretically and never directly observed. The radiation from any black hole of stellar mass or larger is so faint that it is utterly swamped by the cosmic microwave background, and will be for an unimaginable length of time. The mechanism in its most compressed form, quantum mechanics, requires that even empty space is not truly empty, but filled with fluctuating fields that can briefly produce pairs of particles. Near the event horizon of a black hole, this process can result in one particle of a pair falling inward, while the other escapes outward. The escaping particle carries energy, and by conservation of energy, the black hole loses energy, and therefore mass, since in general relativity mass and energy are equivalent. Over time, the black hole loses mass through this process and eventually evaporates completely. The rate of evaporation depends on the mass of the black hole. Small black holes evaporate quickly. Large ones evaporate extraordinarily slowly. A black hole with the mass of the Sun would take approximately 2 × 10 to the power of 67 years to evaporate fully. Supermassive black holes, like the one at the center of the Milky Way, which has a mass of about 4 million solar masses, would take on the order of 10 to the 83rd years. These are, again, numbers that have the form of numbers without having the feel of them. The era of black holes runs from roughly 10 to the 40th years, after proton decay has cleared away the last ordinary matter, to roughly 10 to the 83rd years or later, when the last and largest black holes finally finish evaporating. This is, by the standards of any timescale yet introduced in this series, the longest era of all. During this era, the universe contains black holes, radiation, and almost nothing else. The black holes are the last objects in any meaningful sense, the last things with boundaries, with event horizons, with an inside that is distinguishable from an outside. They are the last places where space-time is doing something interesting, where the geometry is significantly different from the flat emptiness that surrounds them. They are the last complicated things. There is something that keeps coming back when I think about black holes in this context. In the context of being the last things, the final structures. They are objects defined entirely by what they do not let out. Everything that made them, gas clouds, stars, mergers with other black holes, the accumulated consumption of millions of years of stellar material, is gone, absorbed, compressed, past any possible recovery of information about it in any direct observational sense. They are, in a very physical way, the universe's way of not forgetting things it has already let go of, except that even they eventually let go through the slow thermal drizzle of Hawking radiation, which carries energy but in a form that, under most current theoretical interpretations, does not carry recoverable information about what went in. When a black hole evaporates, the matter that fell into it is not released in any recognizable form. The radiation that comes out is thermal. It has the statistical properties of heat, not the structured properties of information. The original matter is, to the extent that we understand the process, lost. This is known as the black hole information paradox, and it is genuinely unresolved. Whether information is truly destroyed, which would violate quantum mechanics, or preserved in some form, which would require an extension of our current understanding of gravity and quantum theory, is a question that has occupied physicists for decades without a settled answer. The black hole does not care about the paradox. It continues evaporating at its own pace, regardless of whether we have understood what it is doing. When the last black hole goes, the universe loses the last object with a significant gravitational gradient, the last place where space curves sharply around something. What remains is an almost perfectly flat, almost perfectly empty space, filled with the faintest possible radiation, the Hawking radiation of the last evaporated black holes, red-shifted almost to nothing by the expansion that has continued this entire time, and with the lightest possible particles, electrons and positrons and neutrinos, at densities so low that the average distance between any two of them is larger than the observable universe is today. The universe still exists in a technical sense. It still has energy. It still has temperature, though the temperature is so close to zero that the difference from zero is expressed in numbers that require scientific notation to hold fractions that small. It is a universe in which nothing complicated is happening. It has been that way for longer than black holes lasted, and black holes lasted longer than stars by a factor larger than stars lasted longer than everything before them. The universe at this point is almost entirely in its last chapter. Almost. The sound of Hawking radiation, if you had 10 to the power of 67 years. It is already happening. Right now, a stellar mass black hole somewhere in this galaxy is losing mass at a rate so small it would require expressing the fraction as a decimal with 67 zeros before the first significant digit. The energy it is radiating is not zero. It is just below any threshold that has practical meaning. The radiation is there. The process is running. In the time it takes you to finish this sentence, a black hole with the mass of the Sun has lost an amount of energy that is effectively nothing by any measure we currently use, and also more than nothing, and also real. The Hawking radiation from a stellar mass black hole today is not detectable. It is not detectable in principle with instruments we can currently imagine. The reason is not the smallness of the effect alone. It is that the current cosmic microwave background temperature, 2.7 degrees above absolute zero, is roughly 100 million trillion times hotter than the Hawking temperature of a solar mass black hole, the signal is completely buried in the ambient noise of the universe. The black hole will not be detectable by its Hawking radiation until the universe has cooled to the point where the background temperature drops below the black hole's own Hawking temperature. For a solar mass black hole, this requires the universe to be incomprehensibly older and colder than it is now. By that point, as established in the previous chapter, ordinary matter will long since have dissolved. The Hawking temperature of a black hole is inversely proportional to its mass. Smaller black holes are hotter. A black hole with the mass of a mountain would have a Hawking temperature of billions of degrees and would evaporate in a fraction of a second. A black hole with the mass of the moon would be cooler, but still far warmer than the current cosmic background. The relationship between mass and temperature is fixed by fundamental constants. The speed of light, Planck's constant, the gravitational constant. These constants do not change. The Hawking radiation is not a theoretical nicety that might turn out to be wrong. It follows from combining quantum mechanics and general relativity in a way that both theories require. The uncertainty is not whether it happens, but what it means, whether the radiation is truly thermal, truly information-free, or whether something subtler is occurring that would require a theory of quantum gravity to fully describe. The black hole does not wait for us to resolve this. It radiates at the rate it radiates. Think about what it means to wait for a process this slow to become perceptible. The current age of the universe is approximately 13.8 billion years. A solar mass black hole takes about 2 times 10 to the 67th years to evaporate. That is roughly 10 to the 58 times longer than the current age of the universe. For most of that time, the evaporation process is producing radiation that is colder than the environment, and therefore undetectable against background noise. It becomes the dominant source of radiation in its local vicinity only after the cosmic background temperature has dropped below its own Hawking temperature, which happens after something like 10 to the 83 years for the largest black holes. To watch a black hole evaporate from beginning to end would require being present across a time span that makes everything that has ever been called waiting look like a moment of impatience. The process is not slow in the way a watched kettle is slow. It is slow in a way that makes the concept of slow reach for something it cannot quite touch. And yet, the process is there. It is running. In whatever sense processes exist in the absence of observers, it continues. The black hole, surrounded by a universe that has grown too cold and too empty to feed it, continues to radiate. The mass continues to decrease. The temperature of the radiation, which rises as the mass falls, because the smaller it gets, the hotter it becomes, rises imperceptibly, then perceptibly, then dramatically, in the final stages of evaporation, when the remaining mass is small enough that the Hawking temperature climbs toward the Planck temperature, and the final evaporation happens in a burst. The last moments of a black hole are not quiet. They are not the long, slow, thermal drizzle of most of its life. The final evaporation is energetic, a rapid cascade of particle production as the remaining mass converts to radiation. For a brief period, brief measured in the scale of the evaporation, which still dwarfs any human time scale, the black hole becomes one of the brightest objects in its vicinity. Then it is gone. No remnant, no cold object left behind, no record of what it was, just the radiation from its final moment spreading outward into the dark, red shifting as it goes, its energy dispersing into the background. The universe after the last black hole evaporates is not a universe in which something has just been lost. The loss was so slow and so total that the word loss has stopped fitting by the time it is complete. It is a universe that has simply arrived at a new condition. The condition is no objects, no structures, no gradients large enough to drive any process of significance. Just a vast, still, cold space containing dilute radiation and the lightest possible matter, the whole thing expanding, the temperature falling, nothing with any particular location relative to anything else that could be said to matter. The thread of the Hawking radiation has been followed all the way to its end. The end is not a wall. It is not a sound. It is more like the last moment before you notice there is no longer anything to listen to. The texture of something being there and then the texture of nothing being there, and the difference between them being so gradual that you would not be able to say when it happened. The universe has been moving toward this condition since the first second. The Hawking radiation was always going to be part of how it got there. It has been doing its part at its own pace, without announcing it, since the moment the first black hole formed. The patience of the process is not a quality of the process. It is a quality of the time scale. Given enough time, even this was always going to finish. It just needed, as these things go, a while after. The state the universe reaches after all of this is not death. Death implies something that was alive. The universe was not alive. It was a physical system, governed by laws that operated consistently across the entire span of its existence, and those laws did not change when the last black hole evaporated, and they do not change in the state that follows. The state that follows is sometimes called the heat death of the universe, and the name is almost entirely wrong. There is no heat in any meaningful sense. The temperature is as close to absolute zero as a physical system can get without reaching it. And absolute zero is not reachable, for reasons that are baked into the same thermodynamics that produced the situation. And nothing dies, nothing event occurs. The universe simply reaches a state of maximum entropy, a state in which energy is distributed as uniformly as possible, in which no gradient of any kind exists that could drive any further process. Maximum entropy is not emptiness. The energy is still there. It just cannot do anything. Think about what it means for energy to be unable to do anything. All work, in the physical sense, requires a difference. A temperature difference, a pressure difference, a concentration difference. Some asymmetry between two states that allows energy to flow from one to the other, and, in flowing, do something. A steam engine works because steam is hotter than the environment. A battery works because one end has more chemical potential than the other. A star works because its core is hotter and denser than its outer layers. Life works because the sun is far hotter than the earth, and the earth can radiate its absorbed energy into the cold of space, and in the gradient between those two temperatures there is room for chemistry to run, for cells to maintain themselves, for everything that lives to find its energy. In the maximum entropy state, no differences remain. Every region of the universe has the same temperature as every other region. No flow is possible. No work can be done. No process can run. This is what evenness looks like taken to its logical conclusion. There is a small qualification worth making. The universe in this state is not perfectly uniform. Quantum fluctuations are real, and they persist even in the lowest energy states. Small, random, spontaneous variations in energy occur everywhere. Always, because quantum mechanics requires them. These fluctuations are not large enough to drive any macroscopic process. They are not a source of hope for the universe. They are just the irreducible background noise of a physical system that cannot be completely silenced. On timescales that are, by now, longer than everything in this series combined, by factors that no longer feel like multiplication, a particularly large quantum fluctuation might spontaneously produce a particle or a small cluster of particles in some region of the otherwise featureless universe. These events are so improbable that their expected wait time exceeds the lifetime of any of the eras described in the previous chapters by margins that collapse language. They are not a revival of the universe. They are statistical noise, but they are real. They are permitted by physics, and they mean that the maximum entropy state is not perfectly still. The universe in this state is still expanding. Dark energy, which is driving the accelerated expansion currently observed, is expected to continue driving it in the far future. The expansion does not stop when entropy is maximized. The space continues to grow. The dilute radiation in it continues to redshift and lose energy. The already vast distances between any two particles continue to increase. This is the thing that does not end, not the entropy increasing, that plateaus at maximum. But the expansion. The universe continues to expand into a future that physics has not fully mapped, into states that may or may not have names, through timescales that are, at this point, genuinely beyond the reach of current physical theory. The universe was always going to go further than we can follow. What does it feel like to contemplate this state? Not from inside it. There is nothing inside it to have feelings. But from here, from a point so early in the timeline that the maximum entropy state is as far from us as the Big Bang is from a fly's heartbeat. It feels like a specific kind of quiet. Not the quiet of a room at night, which is full of small sounds you're not attending to. Not the quiet after a sound, which still has the shape of the sound in it. A different kind. The kind you try to imagine and cannot quite get there. The kind that does not have an edge you can find because there is nothing different on the other side of it. This is the after. Not dark, not cold, not empty, in the way a room is empty when the furniture is gone and someone might come back. Just the steady, permanent, law-abiding state of a physical system that has finished everything it was going to do. It was always going to be like this. The first second of the universe contained this outcome the way a held breath contains the exhale. The laws were set. The direction was set. The only question was the duration, and the duration was always going to be longer than anything we could name. The after is not a tragedy. It is a completion. Whether those are the same thing depends on something physics cannot measure. The first chapter, remembered from the end. There is a specific quality to understanding something that you cannot undo. Not the quality of learning a fact. Facts can be forgotten, misremembered, revised. But the quality of having grasped a shape, having felt the proportion of something, having let a large idea settle into a part of you that does not send it back. This series has been trying to produce that quality, not through argument or explanation, but through time, spending enough time with each part of the idea that the parts begin to relate to each other. the way a room begins to feel like itself after you have been in it long enough, not because anything has changed, but because you have stopped noticing what you brought in with you. Go back to the beginning, not to the beginning of the universe, but to the beginning of the first chapter, the dark room, the particular quality of the late hour, the tiredness in the body that was identified as entropy at biological scale, the same direction, the same process, the same impossibility of reversal without input. That was the smallest version of the idea, the version that fits in a hand. What the subsequent chapters were doing was widening the same picture without changing it. The entropy in your body tonight is the entropy in a cooling cup, is the entropy in a cooling star, is the entropy in a cooling universe. The scale changes by factors that break language. The process is the same process. You're a local instance of a universe-wide tendency, running at biological rate, temporary in the way all organized things are temporary, making the same general transaction that everything from a proton to a galaxy is making, spending stored order, releasing it as heat, moving in the direction that everything moves. The name for the end state of this process is thermodynamic equilibrium, maximum entropy, the heat death, wrongly named but recognizable. It appears in the last chapter as a state, as an after, as a kind of completion that physics can describe but cannot evaluate. The word will not appear again. What it leaves behind in the space of this final chapter is not the concept but the distance. The distance between here, you, this room, this late hour, the body that is warm because it is spending itself, and there, the maximum entropy state, the even dark, the after. The distance is not a number, or rather, it is a number, but the number does not produce a feeling. The way the distance to the nearest star is a number that does not produce a feeling of distance when you say it out loud. The mind receives the digits and does not know what to do with them. What it produces instead of a feeling is something more like a posture, a way of holding the information. The universe is large in time the way it is large in space, and the largeness in time is, in a way, harder to hold because time is the dimension you are inside of, the one you cannot step back from to look at. Space you can at least imagine looking at from outside. Time you cannot. You are always in it, always at the same point of it, unable to see the extent of it from where you stand. The science says the extent is large, larger than anything we have words for. The stellar era is a brief early phase. The degenerate era that follows it runs longer by a factor that makes the stellar era a rounding error. The black hole era runs longer than the degenerate era by a larger factor still, and beyond all of that, the quiet after, and inside all of that, somewhere near the very beginning, in the small warm period when stars existed and chemistry worked and life found its foothold, you, here, now. The thing about coming back to the beginning from the end is that the beginning looks different. Not wrong, not smaller. Different in the way a word looks different after you have heard it used in many contexts. The late night room, the tired body, the cup cooling on the table, these things have not changed. But they sit now inside a larger frame, and the frame changes what you notice about them. The cup is cooling because everything cools. The body is tired because organized systems spend themselves. The dark of this hour is a very local, very brief version of the dark that the universe is heading toward, across timescales that dwarf every timescale in this series by margins that still require scientific notation. None of this makes the cup less real, The cup is exactly as real as it was before you knew any of this. The tiredness in the body is exactly as real. The room is exactly as real. But real now has a frame around it. A large, patient, impersonal, accurate frame. The kind that changes not what you see, but what you understand about the fact that you are seeing it. There is a question this series asked in its first chapter and did not answer. What happens when the universe runs out of things to do? Now you have most of the answer. The universe does not run out all at once. It runs out in stages, each stage lasting longer than all the stages before it, each stage leaving behind a smaller list of things that can still happen. Stars end, matter decays, the last gradient disappears, the expansion continues into a state that physics can name but not fully describe. What is not in that answer, and what this series has been quietly honest about not being in that answer, is the part about meaning. Whether the universe's completion is a tragedy or a fact, or something else that does not have a name, depends on something that physics cannot measure, has no instruments for, has no equations that touch. The science describes the process with extraordinary precision, and stops exactly at the threshold of what the process means. That threshold is where you are right now. At the end of what can be said about the shape of things, standing at the edge of what can be measured, holding a large and accurate picture of a universe that began in a state of extraordinary order and has been spending that order ever since, and is currently spending it in you, tonight, in this room, in the specific and temporary and non-recurring arrangement of matter and energy that is you being here, knowing this, at this late hour, on this particular night. The universe will not remember this moment. There is no mechanism for it. But the moment is happening, completely and actually, and in the only present tense there is. That might be the most accurate thing in this entire series, and it has not quite finished settling yet.